Well, let's take a look at a wire. It's bent into a semicircular shape. Where's the center of mass? For a change, we're expecting the center of mass to be above the halfway point rather than below it, because most of the mass of this metal wire is located up here. What variable are we going to use to integrate? We can't use x because nothing's really going straight. We can't even use y, even though that's precisely what we're looking for, the y location of the center of mass. We're going to have to use something that involves arc length. And arc length, as we remember from our definition of the radian, S equals r theta. As usual, we're going to start with defining our mass density. Lambda for linear mass density, because this really is a one-dimensional object, is still m over L, total mass divided by total length. But instead of being dm dx or dm dy, now it's going to be dm ds, such that our friend dm, which we're going to need to get rid of soon, is now lambda ds. What's lambda? Experience from yesterday leads us to define it early on. We said lambda was the total mass, which we're not given, we can only hope it cancels out, divided by the total length. What's the total length of this semicircular wire? Let's see, well, the total circumference is 2 pi r, so the total length is going to be pi r. That ought to come in handy sooner or later. So, let's take it away. We want to find the vertical location of the center of mass, and our formula for that, 1 over the total mass times the integral of y dm. In polar, y may turn out to be a problem. We'll hold that for the moment. Let's first get rid of dm, as we always do. There we go. dm is gone. dm is lambda ds. Now, taking a look at that graph, that still doesn't give us very good limits of integration. ds is better than dm, but it's still not good enough. We're trying to go from here to here. That's not s, that's theta. Wait a minute. If s equals r theta, then ds ought to equal dr theta. Wait, look at this. We have a wire. It's bent into half a circle. All the mass is on the edges at a constant value of r. r is constant, it does not change. ds is r d theta. And that is going to make life much easier up here. We have not just 1 over m, but pull out that nice constant. We have y r d theta. Now we've got 2 constants to pull out. We can pull out the r, and we can see what the lambda equals. Let's pull out that r. We had lambda r over m, left over with y d theta. There's so much we can do here. We now know our limits of integration. We are going from theta equals 0 to theta equals pi. We know that lambda is m over pi r, and then we had the r over m. Isn't that nice? We have our integral from 0 to pi of y d theta. That's not nice, but y in polar is r sine theta. D theta. Oh, wait, it's not just any r sine theta. We're not here. We're not here. We're not here. This whole shape is hollow. Everything is at a fixed radius. There goes another constant we can pull out. And we're left with a tidy little r over pi. Antiderivative from 0 to pi. Sine theta d theta. There's our constant. Whose derivative is sine? Bless my soul. Sine is the derivative of negative cosine.